Hello, everyone. Welcome to the unit on meteorology. We're going to get to learn how the weather works. This could be useful. So, meteorology is the study of the changing conditions of the atmosphere, how the atmosphere moves day to day. Weather is the short-term condition of the atmosphere. Weather changes over the course of hours. The major weather variables. Think about what the major weather variables are. Okay, the one that affects us the most is the air temperature. If it says it's 0 degrees outside, you really need to take that into account when you're getting ready for your day. Um, if it says it's 80 degrees outside, again, you're not going to appear the same. If you have any intelligence at all, you're going to dress appropriately. You're going to conduct your activities appropriately based on the temperature. You're not going to take your boat out when it's 0. You're probably not able to even get to the water if it's 0. Air temperature matters a lot. Now, air pressure you might not think of as being a major factor in your day-to-day life, but air pressure really pushes these systems around and causes the weather that we have. As you get injured, you will find, like old people often report, when the air pressure goes down, they can feel it in whatever part of them is injured. It actually causes changes internally to your body that cause you pain. Humidity. Humidity makes things happen. When air is very dry, uh, it's one way. When air is very humid, it can produce a whole host of very intense weather conditions. Rain and snow, hurricanes, thunderstorms, all of these things based on humidity in the air. And then, of course, wind direction and speed. I remember hearing years ago that the murder rate in New York City doubles on a windy day. Can you imagine such a thing? But wind really does affect us greatly. And when wind gets going really severely, we need to worry about that. So let's think about where Earth's atmosphere came from. The early atmosphere was very, very different from the atmosphere we have today. Our atmosphere originated from outgassing from volcanoes. So most of that outgassing was water vapor, hydrogen, carbon dioxide, and nitrogen. Water vapor, well, that helped create the oceans. Hydrogen is the lightest gas, so much of it escaped to outer space. Carbon dioxide, well, the oceans absorbed some, then organisms. Nitrogen, nitrogen didn't do much. Once it's in the atmosphere, it just kind of lingers. Oxygen was put in not originally, but after life started, ocean cyanobacteria began producing oxygen, a very toxic gas, and it really changed everything. And everything on Earth has to know how to deal with the toxic oxygen. And as of course you know, we made it work for us. So the modern atmosphere is a direct result of billions of years of biologic activity affecting it. Only biologic activity could keep oxygen in the atmosphere the way we see it today. Currently, the atmosphere is mostly oxygen and nitrogen. There are trace amounts of carbon dioxide and argon. Argon has about 1%. Carbon dioxide is truly a very tiny amount, but that means as mankind adds more, it can easily change the amount of carbon dioxide, and that's involved in the balance on Earth. When we look at something like a volcano, the various things that come out of a volcano, nitrogen goes to the atmosphere and just stays there. Water can go to the oceans. Hydrogen escapes. Some water can be affected by sunlight so that it breaks apart. The hydrogen escapes. Oxygen stays in the atmosphere. Oxygen and carbon dioxide are involved with photosynthesis, and so that keeps a balance in the atmosphere. If we look at the atmospheric gases, 78% is nitrogen, 21% oxygen, and then the other main ones are, look at the tiny amounts of CO2. And argon is almost a whole percent. So that's what our atmosphere currently is doing. So layers in the atmosphere. The atmosphere has a variety of layers in it, and it's divided into generally four layers based on what happens to the temperature as you go up through them. For example, in this troposphere, this is down on the ground. This is where we live. As we come up from the surface, the temperature decreases. Well, why? Well, the sunlight comes through the entire atmosphere and hits the ground. The sunlight then turns into heat. So it heats the lower part of the troposphere. As you get away from the source of the heat, which is the ground, of course, the temperature goes down. So then we get into the stratosphere. Now, why would the stratosphere warm up? There has to be some of the sunlight being absorbed inside the stratosphere. And indeed, the gas ozone is doing that. Ozone absorbs ultraviolet light, removing a lot of it from the sunlight. That is what makes life on dry land habitable here on planet Earth. So the ozone warms up the stratosphere. Wherever the ozone layer is, it's warmed up as you go through it, and that's why we have the stratosphere. When you're out of the ozone, then the temperature starts going down again, and you are in the mesosphere. Way above the Earth, you're into the region of kind of the solar atmosphere. That would be the thermosphere. As you go up through that, now the temperature increases again. So this picture is ridiculously exaggerated, but we can use it to talk about things. So the troposphere is 10 kilometers high. Now, notice this is so exaggerated that the entirety of the atmosphere, all the way through the exosphere, would be in this little region here. So please know this is a tremendous exaggeration. After the troposphere, you have the stratosphere, then the mesosphere, thermosphere, and the exosphere is just where it gets super, super tiny. So here's what's happening in the atmosphere. Again, there's an exaggeration going on here, but it's not so bad when you look at the Earth being essentially flat down here. All right, so we're looking at a tiny portion of the Earth if it would still look flat. So that's a little bit more reasonable. So troposphere, as you go up, temperature goes down. Here's that ozone layer. As you go up through that, the temperature increases because you're absorbing ultraviolet light. Above the ozone layer, the temperature goes down again. Now, the atmosphere is just thick enough here, so anything flying through it really fast, like a meteor, will burn up. Above the mesosphere, to the region of the thermosphere, this is where you'd have auroras go on. You have high energy particles from the sun bombarding this area, and that makes the temperature rise. And above that, you have the extremely thin atmosphere, which we'd call the exosphere, and satellites can go through there. Why? Because the atmosphere really is just, it's hard to even find atoms of the atmosphere there. Now, here is Brian McCandless in his flying suit from the space shuttle back in, I believe, about the early 80s. But that's not what this picture is for. Please look right here. This is the edge of the Earth. This is a zoomed in picture. He's actually quite a ways from the space shuttle here. This is a zoomed in picture. So here you could see the atmosphere of planet Earth. And look how incredibly thin that atmosphere is. From a distant picture of the Earth, you can't see the atmosphere above the Earth's surface at all. And here you just see a faint band of blue. On your reference tables, it tells you most of what you need to know about the atmosphere. So over here, you have everything about the temperature. So as you come up above the surface of the Earth, the temperature drops, and you can see the average coldest part of the temperature there is about minus 55 degrees Celsius. And then as you go up through the stratosphere, it gets warmer and warmer till it finally stops increasing. Every place between layers, like when it stops decreasing above the troposphere, you have the tropopause. When it stops increasing above the stratosphere, you have the stratopause. Then the temperature goes down again. You can see how low it gets to about minus 90. You have the mesopause. When the temperature stops decreasing, it starts increasing again with really no end in sight. You're in the thermosphere. Notice this, the atmospheric pressure, the numbers go down by a factor of 10 for each number. So The pressure here is 1 atmosphere of pressure. That's the normal air pressure you're used to. The first thing we see is 10 to the minus 1. That means 1/10 of the atmospheric pressure. That's what you have, somewhere early in the stratosphere. Not too high up, well, about midway through the stratosphere. It's about 1/100th, 10 to the minus 2. 10 to the minus 3, that's what we have in the mesosphere. So that's 1,000th of the atmospheric pressure here. And we drop off the list at 1/10,000th, and that's still in the mesosphere. So you can see we have a lot of air right down in the troposphere, and it gets amazingly dispersed, diminished tremendously as you go up, not too far above that. The other notable thing is look at the water vapor. All the water vapor to speak of is in the troposphere. We cannot measure much water vapor at all in the stratosphere. So we do occasionally get hit by things. Our atmosphere protects us from the small things. It does not protect us from the large things. Here in Quebec, you have a huge circular depression left over by a large object, not this large. That would end life as we know it on Earth. But this is a large object having left a crater that then filled in with water and is actually used for hydro power in Canada. So, like I said, the reason for the temperature changes in the troposphere, distance from the surface, the source of heat, is increasing. In the stratosphere, the ozone is absorbing ultraviolet light, so it releases the energy as heat, so it warms up. Mesosphere, there's no ozone present. You're far from the surface, so there's not a source of heat in the mesosphere. It gets really cold. And above that, now you're entering the region of solar activity. Movement of energy. Well, more sunlight, therefore heat, falls on the equator and less falls on the poles. The air moves the heat from the equator to the poles. Without circulation of the atmosphere, the poles would become much colder and the equatorial regions would get much hotter. But what is the main reservoir of energy in the air? Surprisingly enough, this is not known by most. Please know this, because it is the water vapor in the air. That's how you carry energy in the air. So look at this. You have huge amounts of sunlight fall where the sun is directly overhead, and you have very little sunlight energy available where the sun is all spread out because it's so low on the horizon. So very hot here, very cold here, and the movement of heat is what drives weather. So temperature changes at the surface. Let's think about what causes the temperature to change at the surface. So this occurs in cycles, and you know this. Daily, it's coolest in the morning and it's warmest in the afternoon. Seasonal, well, it's cold in the wintertime, it's hot in the summertime. And these are cyclic changes. If you have clouds, it's like pulling a blanket up over you. In the summertime, if you hold a blanket up, it'll stop the sunlight from hitting you, so you won't get as hot, believe it or not. In the wintertime, it'll keep the heat from you from escaping to space, so it'll keep you warmer. Clouds work the same way. So they reduce temperature during the day by reflecting sunlight back to space. They increase temperature at night by reflecting the heat back to the ground. So look at this. Here's a steel tank car crushed. What could possibly crush a steel tank car? Now, it was empty, of course. Well, was it really empty? When it was sealed, and they didn't leave a vent open on it, when it was sealed, it was really hot in baking sunshine. So when it's really hot, think of it, the atoms are vibrating really fast. That means the atoms push apart, kick a lot of the atoms right out of the tank car, leaving quite low air pressure inside. At that point, the tank car must have been sealed. And then it was put on a train and carried far up north, where it got really, really cold. Now, the atoms inside the car then are vibrating very slowly, and they can get much closer together. but there's no way for more atoms to get in. If a vent had been left open, more atoms would have been sucked in, and the pressure inside and outside could have balanced. But the vent was closed. So with the atoms inside not vibrating fast, they're also not hitting against the side of the tank very hard, not exerting much pressure on the outside of the tank at all. Meanwhile, the super cold atoms around it are so cold, and they're banging on the outside of the car. There's so many of them that they crushed the tank car. Air pressure. Air pressure changes can make a big difference. So all that is to show that air has weight. The ocean of air extends many miles above us. We live at the bottom of this ocean, and because of all the weight of the air above us, we live at a pressure of 14.7 pounds per square inch. That is to say, if you took a square inch and turned it into a square rectangle that runs all the way up through the atmosphere, that square inch rectangle would have 14.7 pounds of air in it for every single square inch. The pressure of the air, therefore, is due to the weight of all of it above us. So as we move up in that column of air, there's less air pushing on us, so the pressure goes down. If you think of a stack of books, where's the paper pressure highest? Right at the bottom. That's exactly what's going on with the air pressure here. Right at the bottom of the air pressure, right at the bottom, the air pressure would be highest. So if we're thinking high air pressure, there's a lot of air molecules next to us. If we're thinking low air pressure, there's fewer air molecules next to us. Makes sense. So air pressure is greatest at sea level, and it decreases with altitude. Air pressure is exerted in all directions. Air pressure is measured by a device called a barometer. So a barometer is based upon air pressure pushing up a column of liquid. A different kind of barometer is an aneroid barometer. It's just an airtight box connected to a calibrated dial. So when more air is pushing on the box, it squishes it, and the dial reads a higher air pressure. Meteorologists measure air pressure in millibars, and we've discovered that the standard sea level pressure is 1013.2 millibars. So that would be the average pressure at sea level. On a weather map, isobars connect places of equal air pressure, just like on a topographic map, iso elevation lines connect places of equal elevation. Here's a mercury barometer, and what we see, the air pushing down on the surface of the mercury dish here forces the mercury up here. Up here, there's a vacuum. So this is an excellent barometer. It measures air pressure as perfectly as you can. What's the downside of it? Well, mercury. We used to have one in the classroom, had to get rid of it because it's filled with liquid mercury. Mercury is toxic enough that you do not want it around. So while it makes a great barometer, I don't know that you would find them very often anymore. What we use instead is an aneroid barometer, and here we have a little can, and that can has a vacuum inside. So when the air pressure increases, it squishes on the can, and you just connect a lever to it. And when the can is squished, the lever reads high pressure. When the can expands, the lever turns the other way and reads low pressure. The key here is not what the air pressure is, but how it's changing. If the pressure is going down, it means you have a low air pressure moving into your area. Low air pressure is connected with storms, raininess, snowiness. Hurricanes have very, very low air pressure. Generally speaking, the lower the air pressure, the more storms you have in store for you. The higher the air pressure, the more you're going to have blue sky, cold weather, very, very dry day. So here is how we use a barometric map of the United States to predict the weather. We know that a low pressure system, that's stormy weather. And as you'll see, we start connecting fronts to that. Fronts are where all the action is. It's between the area between two air masses, and it's where you have all the things you'd call bad weather, storminess, uh, winds, and all that, generally connected with very low pressure. But more than that, air around a low circulates counterclockwise, right? Low towards the lower numbers on a clock face, counterclockwise. Well, if you think about that, that means here you're bringing air up on this side of the low, you're bringing air up from the south, meaning that it would warm areas here when the low is approaching. Behind the low, you're bringing air down from the north, so it would cool areas after the low passes. Starts to make sense, doesn't it? Around a high, you have air circulating clockwise. Now, you get high pressure when air is sinking down to the ground. That kills clouds. You have blue sky, generally considered nice weather, although it can be quite cold as well. But another key to remember is that around a high, air circulates clockwise. So behind the high, you'd have warmer air coming up from down south. In front of the high, you'd have colder air being pulled down from up north. So using a high and a low pressure map, you can kind of figure out a lot about what the weather is up to. That's why pressure is so important to understand what's coming with the weather. And here is what causes all the pressure. Each square inch presses down with the weight of the air above it. So it's 14.7 pounds per square inch. How hard does it press down per square foot? Okay, this will make you crazy. Well, how many square inches in a square foot? How many square inches in a square foot? Don't say 12. It would be 12 times 12, or 144. So if we take 14.7 and multiply it by 144, we have 2,117 pounds, or more than a ton of pressure for a square foot. Think about that. That's an enormous amount of air pressure. How can we survive? Well, air pressure is exerted in both directions, in all directions. So it's being exerted from under us as well as above us, so it's not exactly crushing us. It is, however, squeezing us, which means you could have a problem if you are not built to withstand this air pressure, and we most certainly are. Everything that evolved here can withstand that air pressure. Think of a deep sea creature with so much more water pressure on it, it's fine for where it belongs. But if you bring it up here, it doesn't do very well at all. It tends to explode a little bit. So you're meant for the air pressure that is upon you, but don't ever think that's a small amount of air pressure. As a matter of fact, one of the ways to understand what the air pressure is, how far underwater would you have to swim to simply double the air pressure? If you've ever swum down to the bottom of a really deep pool they use for diving, you're about 10 to 12 feet, and you can tell that pressure is pushing on your ears. You can really feel it. It's a lot of air. It's a lot of water pressure on you. No, you haven't doubled the pressure on you. You'd have to swim down 33 feet underwater, a really amazing depth, 33 feet underwater, to simply double the pressure you're under. That's impressive. So that's a lot of pressure. So what are some factors that would affect atmospheric pressure? Well, clearly altitude. Air is becoming less dense with an increase in altitude. So why does the air pressure decrease with altitude? Think of it again as a stack of books. Where's the paper pressure highest? On the bottom, because of all the paper on top of you. If you went up higher in that stack of books, why does the paper pressure decrease? Clearly you have fewer pages on top of you. Same exact thing with air pressure, except air is very squishable. So when it squishes, the air is really dense on the bottom, and the density decreases very quickly as you go up. Temperature, well, that's going to affect air pressure. When air molecules cool, they contract. They can get closer together, therefore more pressure. When you heat them up, they vibrate faster, they expand, therefore less pressure. Humidity, well, now, this is confusing. Humid air is lighter than dry air. That's going to take some explaining. When you add humidity, why would that make air lighter? All right, measuring air pressure. Now, believe it or not, I have to teach you how a straw works because a straw does not work the way you think. When you drink through a straw, you're reducing the pressure inside the straw. That's it. The higher pressure on the surface of the liquid pushes the liquid up through the straw. So you do not suck the liquid up through the straw. Rather, you reduce the air pressure in the straw and the liquid is pushed up. Air has enough pressure to force the liquid up a straw 33 feet long. 34 feet, there is no pump on earth you could get that would ever draw air or would draw water up a straw 34 feet long. It simply couldn't happen because it cannot suck water up. It reduces the pressure to zero, and air pressure on the outside can push it up 33, and that's as much as it can push it up. So it's exactly how a barometer works. As the weight of the air changes, it pushes the liquid up to different heights inside the barometer. Pretty cool. So this is exactly how how that straw is doing it, right? When you are sucking the air out, well, you're not really. You're drawing the air into your mouth, but you're reducing the pressure. That's all you can do. So lower pressure in the straw means the pressure outside pushing down is higher pressure, and it pushes the liquid up through the straw. When you're going to report air pressure, you need the millibar system. A long time ago, they figured the average air pressure, and they called that 1 bar. So 1 millibar is a thousandth of a bar. As we got better at figuring everything out, we realized that the average air pressure is about 1013.2 millibars. So in your Earth Science reference table, there's a chart that will convert millibars to inches of mercury. The inches of mercury is how high it would have risen in a mercury barometer. So pause this for a second and go grab your reference table. I'll wait. Come on, you got to grab your reference table. On page 13, on the right side, you'll see the pressure, how to convert pressure from millibars, MB, to inches of mercury, labeled IN of Hg, mercury. All right? So, and they're asking you to convert. You'll have to do this fairly often. So if you look at 29.94 inches of mercury, find 29.94 going up the right side. Say you see 29.9 above it, you see 30.0. So you can see 29.94 is almost halfway up that. Look over to the other side. You'll see it's 2 dashes down from 1016. Correct. It would be 1014 millibars. How about 30.20 inches of mercury? Well, 30.20, you're going up, and you see exactly where it says 30.20. And go across, look at the closest bar to that, and that's about 1023. It's a little less than that, but that's fine. How about 30.16? Are you following along? Please make sure you do this. 30.16, well, you see 30.10, and above that is 30.20. There's 10 marks between them, so each mark must be one of them. So 30.16 brings you just a little bit above 1021 millibars. Doesn't have to be exact, but get it as close as you can. So now going the other way, if you look at 1,000 millibars, you read directly across from that. Lower than that, you see 29.5, and you could count up 29.5, 1, 2, and 3. So 29.53 inches of mercury. How about 984? 984, you read directly across. Look, it's right at the bar between 29.00 and 29.10, so that must be 29.05 inches of mercury. And 1026, all the way up near the top, 1026 gives us, look right across, that is 30.30 inches of mercury. Please make sure you know how to do that. That's a whole lot of the questions. Well, that's a lot of the questions that you'll see on exams and such like that. Very simple, just converting the pressure. All right, some things that should be nice, simple review questions now. So, first of all, why does the temperature decrease with altitude in the troposphere? Well, what are you getting away from? The sunlight comes through the air, heats the earth when it hits the earth. It doesn't really heat the air when it goes through it because it goes through it. It doesn't go through the earth. It stopped, so it all turns to heat. You're getting above the earth, which means you're getting above the heat source. So, as you go up in the troposphere, it's getting colder. Why does the temperature increase with altitude in the stratosphere? What's in the stratosphere that could be absorbing some of the radiation passing through it? Ozone. Ozone is absorbing that ultraviolet radiation. Thank it for your very life. The sunburn you get would kill you if it wasn't for the ozone layer. So the ozone layer is absorbing that ultraviolet radiation and it turns it to heat. So, big time. In what form is most heat energy stored in the atmosphere? Right? It's not in the air. It's in the water vapor. How can that be? Imagine this. Take a pot of water, right? A cold water, put it on the stove, crank it on maximum. It'll take about 10 minutes till it's boiling, ballpark. If it takes about 10 minutes till it's boiling, it will be well over an hour till you've evaporated all of it away. Think about that. So boiling, it's already as hot as it's going to get. You can't get it any hotter. So what are you doing with all the heat you've been adding for that more than an hour? You're turning the water into water vapor. Stays the same temperature, just converts water to water vapor. Nature is reversible. That means when you condense a pot's worth of water vapor out of the air, you release all of the heat that it took for that hour and 10 minutes or so to evaporate that whole pot of water. You're releasing all of that with each pot of water you condense out of the air. Think about how many pots of water come out of a thunderstorm. So many. Each one released that much heat to the air. You get a sense of why thunderstorms are so violent now? That's a huge amount of heat. That's nuclear bombs worth of heat being released to the atmosphere from a good-sized thunderstorm. Makes you think. Okay, so what happens to air pressure as altitude increases? Well, is there as much air on top of you anymore? No. So it's not pushing down as hard. So air pressure decreases. So where is the air pressure highest and why? Okay, where's the paper pressure the highest in that stack of books and why? I think we've been over that. So do we have a sense of how much 1 square foot of air pressure can exert on the ground? It's over a ton. Pretty impressive. So how come the windows in the classroom, which have many, many square feet, how come they don't explode inwards? They have like 30, 40, 50 tons of air pressure outside pushing in. Are the windows really that sturdy? Of course not. What's the air pressure inside the building? Exactly what it is outside. So it pushes back just as hard. If it were to be even a little bit different, those windows would explode. So can you draw and describe now how a straw really works? You're not some old toady who thinks you actually suck the liquid up, are you? What a maroon. That would never happen. Rather, you reduce the air pressure inside the straw. Higher air pressure on the outside pushes the liquid up through the straw. And that is how it really works. So here's a connective thing showing all of the ways the atmosphere affects everything. It's pretty good. Take a look at it. The only thing I have to correct is down here. They said scattering of longer wavelengths of light causes the blue sky, and that's wrong. It's scattering of shorter wavelengths of light. But everything else seems okay. Pause it, take a look at that, connect up those ideas. Hey, thanks for watching. Bye-bye.